Okay, hello everyone, welcome back. So in the previous class, we have shown you with some examples for the logical laws we can use to simplify or optimizing the query logic plans. And in this page, we can further show you with some other laws for optimizing the queries, which when involving the projections. And let's assume we have two relations R and S, and we want to do the projection of some attributes denoted by the set M. This M denotes the set of attributes we want to do the projection, right? And we are working on two relations, R and S, and we are joining them together prior to do the projection. So actually, this kind of operator or this kind of operation is equivalent to what? It is equivalent to the projection of some attributes N. N denotes a subset of attributes, and inside it we have two other projection operators. Projection P denotes a subset of attributes on the relation R, and the joins with the projection Q also denotes a subset of attributes of the relation S. Here the M, P, Q, they are all the set of attributes. Specifically, this M, P, Q, they cover some appropriate subset of attributes from this M, this set. So you can compare them with each other, right? So for the first one, we directly compute the joins between R and S first, and then applies projection to project some desired attributes. However, for the right-hand side, prior to the projection of N attributes, this set, we do the sum projection before, right? Prior to that, we projection P, Q first from R and S, these relations, and then we do the projection of N and these attributes. So you can see, right, compare with each other, you cannot analyze of the cost for computing these operations. So for the left-hand side, given two relations, R and S, if we assume this R and S, they have lots of attributes, they are very large in terms of attributes. And if we compute the joins between them, this relation, result relation will be very large, right? And then we can do the projection based on this larger relation to get some desired attributes. We can do in this way, it is okay, right? However, the cost will be very large or very high. And on the right-hand side, we have the projection of P attributes from R first. If we have R to be a very large relation with lots of attributes, we can just project some desired attribute first, is P, right? Similar for the S, if this S is also a very large relation with lots of attributes, we just project some subset of the attributes first, and then we do the joins. This join will be the cost will be very low, right? Because we are doing joins between two relations with a very small number of attributes in state after we do the projections. And then we can do further projection of the desired attributes N, right? So compare with the left-hand side, the right-hand side can reduce the time cost as well as the I/O cost or not, right? Because we can reduce the cost on the joins between two relations with a small number of attributes only. It can reduce the I/O cost or not. This is one of the example. We can show you with example how to design this NPQ, this sets specifically with some concrete examples. Another law we have here is a projection of M. Inside we have a projection of N. Both M and N denoting the attribute sets, and we are working on the relation R. This will be equivalent to the projection of M intersection with N on the relation R. And you can compare them with each other, right? So for the first one, we have two projections. However, for the right-hand side, we have only one single projection given relation R. And in some cases, it can also reduce the time cost as well as I/O cost, right? Because for the first one, we have saved the intermediate result for the first projection NR, right? And then we can do one more projection. However, for the right-hand side, we can do one single projection directly on R. We don't need to save and store any intermediate result at all. Okay, so at the bottom of this page, we also have an example. Let's assume we have two relations R and S. This R has A, B, C, D its attributes, and S has E, F, G attributes. And we have an operation or we have an expression to be the projection of A, B, G. A, B, they are from this R relation, G is from the S relation, and we are working on the joins between R and S. The join condition is D equals to E, right, between R and S. This will be, similar to this one, right, projection M on R and S, the joins. And then we can redesign this kind of expression in another way according to the law we show here. Right? We can redesign this expression in another way as a projection on some attributes. Inside we have projection of some attributes on R and join the projection of attributes on S. Then how can we do this kind of design as attributes for its question marks? So we can further check the design attributes will be A, B, G. Right? A, B is from R, G is from S. Therefore, here we can design its question mark to be what? To be A, B, and D, right? Because for the joint, we may require D as attributes. So here it can be A, B, D, right? For the relation R. To this question on the relation S, it can be what? It can be G and E, right? G is the design attribute, the G here, right? E is one attribute for the joins. Here we can do the projection of the GE, right? And we can do the joins between them according to the shared attributes. And then we can further project some design attributes A, B, G for the first question mark, right? So according to the rules, we can design this question mark with some design attributes step by step according to the expression we showed before in this page, for example, right? And you can go over this example again by yourself and write this expression on the paper to compare them with each other to see if they can get the same result or not.